This is Jason McIntosh of McIntosh Applied Engineering. I'm going to spend some time showing you how to model a microphone using the Aries Acoustic Modeler. The microphone design I have in mind is something you might find in a consumer electronics product such as a cellular phone or a tablet. This diagram shows roughly what I have in mind for modeling. The gray area is meant to be a plastic wall that the sound is going to pass through. The sound is coming from the left, it's going to pass through this port and reach this microphone and be picked up by the microphone. The green rectangle is meant to be the microphone. So this kind of shows how the sound might come in, pass through that port, pass through a small volume between the plastic and the microphone that's necessary just for spacing requirements, and then the microphone element itself. To model this, we're going to need to know some geometry of these of this port and the volume, and something about the microphone. Here, I'm making some assumptions about how big this port is going to be. I'm assuming it has a 1 millimeter diameter and it's about 2 millimeters long. The volume between the port and the microphone, I'm assuming, has a diameter of about 5 millimeters, and the gap between the plastic and the microphone is about 2 millimeters, or that cylindrical volume will be about 2 millimeters high. This slide shows the microphone that I have in mind. It's a MEMS microphone with an exterior sensing port through its metal cap. Here, this shows the dimensions of the microphone. That port in the metal cap is 0.7 millimeters in diameter, and the metal is about 0.1 millimeters long. I need to estimate how much air volume there is underneath this cap inside the microphone. To do that, I'm going to use the exterior dimensions of the microphone, which are 2.5 by 4 by 1.5 millimeters high. That ends up being 15 cubic millimeters if you multiply it out. I'm going to assume that roughly a third of that overall volume is airspace inside of the microphone. So 1/3 of 15 is 5, or a total of about 5 cubic millimeters of air. That's what I'm going to assume. So with those port and volume dimensions, I'm going to go to Aries and build a model of this. Here's the Aries start screen. I'm going to agree to the disclaimer, and I'm going to go to the new modules menu and create a new modeler module. Screen starts out blank, so we need to start populating it with the elements we need. Most of them are going to be found in the acoustical menu. So I'm going to start by adding the circular port, which will connect the outside world to the microphone. I'm going to use a volume element to simulate the volume between the microphone and the plastic. I'm going to choose an omni microphone element to be the transducer that's going to convert the pressure to a voltage signal. And the microphone element generates a differential voltage across these terminals. So I need to have a ground to produce a voltage reference. So I'm going to connect these up now. And I'm going to go ahead and enter the parameters for these three simple elements. So I'll start with element number 1. We said its length was 2 millimeters and its diameter was 1. So I'm going to change its diameter to 1. I'll go on to the volume element. We said its diameter was 5 millimeters and its height would be 2. If I press enter here, this dependent parameter vol for volume gets updated, and it's being plotted, it's being shown in units of cubic centimeters. We can easily change that to cubic millimeters, which is more appropriate for the sizes we're dealing with, and it comes out to be a little under 40 cubic millimeters. So we know our microphone is about 5 cubic millimeters, so most of the volume right now is being is in this airspace between the plastic and the microphone. So I'm going to click on the microphone element and update its parameters. If you don't know what these parameters are, you can right-click on the element and bring up a menu. About halfway down, there's going to be a help entry for that element. In this case, it's saying Omni microphones. That'll bring up a dialog box that shows you what the parameters mean and provide you with some text about what the actual element is doing. And it's showing here that D naught is the diameter of the port leading into the interior volume. So we know what D naught is now, and we entered that as 0.7 millimeters. We said the metal was 0.1 millimeters thick, which is already the case, and this does not have any acoustic resistance material covering the port. So we're almost ready to run this model, but we need to add some more elements to it. Right now, this model is not being excited by anything. And if we solved it, everything would be 0. So we need to add a pressure source to excite this system. So that'll generate some pressure and some voltages out of the microphone. And we also want to graph the results. So I'm going to create a graph element, connect that up to the output terminal, the electrical output terminal of the microphone. I'm going to right away, before we solve anything, I want to extend the frequency range out to 20 kilohertz. By default, Aries only goes up to 10 kilohertz. And I'm going to change the number of points to 2,000. This is a small model. It'll solve very quickly. So adding the extra number of points will just make the graph a little smoother around the resonance. So now that we've done that, I'm going to hit calculate, and I'm going to pull the graph window over. This graph window was created when the graph element was made. So the graph is auto scaling out to 100 kilohertz right now. We want to change that to only scale out to 20 kilohertz. And this line is rather thin. It's probably hard to see in this video. So I'm going to go back to the main Aries window, go to element parameters, select the graph, and I'm going to set the line weight to 3. And when you hit the set all button, that'll set all the buffers to 3, to a weight of 3. Also under the access range, I'm going to change this to go from 100 to 20,000 hertz. Hit enter, it'll update the graph. I'll pull the graph up. And now we have a little bit better scaling here, and the line is nice and thick, and the resolution is showing that peak nicely. When we do microphone designs, we typically want to see what the deviation is from the passband value. Right now, due to the sensitivity of the microphone, the passband value is coming out at minus 42 dB volts. So we'd really like this to be 0 dB volts. To do that, I'm going to go back to Aries, and I can either change the sensitivity of the microphone, or I can just add 42 dB to the pressure that's exciting the system. I'm going to do that instead. So I'm going to type in 94 plus 42. You can type in mathematical equations for the parameter values. Hit calculate. Let's go back to the graph. And now the passband is at 0 dB. And we can see that we're getting over 20, upwards of 25 dB of deviation from 0 at the resonance. Suppose our design goal is to design this for a wideband communication device. Wideband audio generally goes up to 8 kilohertz, which is out here. So right now, with our current volume and port dimensions, we've got a strong resonance right in the middle of our passband. We want to push this resonance up in frequency so it's as flat as possible out to 8 kilohertz. To do that, we have basically two options. We can make the volume smaller, or we can make the port bigger. I know this because I've built so many of these models. If I go in here and I iterate on the diameter of the volume, it'll create a series of curves, and this is showing me what happens to the resonance as the volume diameter changes. When the diameter is small, the resonance is pushed up in frequency, and when the diameter is large, the resonance is pushed down. So a smaller volume is going to push the resonance up. That's what that sensitivity showed us. I'm going to go back to Aries. I'm going to hit calculate so that we're going to replace that iteration with just a single curve. And I want to decrease the size of this volume. Before I do that, I want to save this original curve to a graph buffer so we can see where we've come from. So I'm going to select the graph element. I'm going to type in original parameters for the name of the graph buffer. I'm going to click the A button, select the check mark so it's plotted. Now I'm going to go in and I'm going to change the size of this volume. We assume that there is a 2 mm gap between the plastic and the microphone. Let's say the mechanics are such that we believe we can decrease that to only a 1/2 mm. So I'm going to change the height to 1/2 mm to decrease the volume. I'm going to hit calculate. I'm going to go back to that graph element again, and we have the original curve, which we copied into buffer A, plotted, and the new curve shown in blue here. We've shifted the resonance up, which is what we expected, but it's only shifted up to just a little under 8 kilohertz. That's still within our pass band. We would like to shift that up beyond 8 kilohertz. So our next parameter that we can change is to increase the size of the port. So if we click on the port, I'm going to change its diameter from 1 millimeters to 2 millimeters. That decreases the mass reactance. If you see here, there's a dependent parameter called mass reactance. Changing that to 2 millimeter diameter actually decreased that. Decreasing the mass shifts resonance up. So before I run this with a new, smaller port, I'm going to go back to the graph, copy our current results in the buffer B, and I'm going to call this small volume. So this is the curve that we achieved when we had a small volume. And now I'm going to hit calculate, go back. We had in red, we now see the curve with a smaller volume, but our current model with a smaller port as well is shown in blue. We've now shifted the resonance up to close to 15 kilohertz, which is well outside of our pass band. If we look at what the frequency response is, if within our pass band, we're still getting a rise in the response at 8 kilohertz. That rise is on the order of about 3 or 4 dB. Now you have to decide for your design whether or not a passband rise of 3 or 4 dB at 8 kilohertz is acceptable for your design. I'm going to go ahead and say that it is, and so we're done with changing the ports and volumes for this, and we've arrived at some ports and volumes that'll be suitable for our design. So we're largely done with the design of the plastic sizes. But let's say we need to add some material to the port to keep out foreign material. So we're going to add some acoustic resistance cloth to this port. If you click on the port, the R parameter here is for acoustic material that you would use to cover the right end of that port. And let's say we're considering a 90 rail material. So I'm going to enter 90 rails here. Before I run this, I want to copy the current model results in the buffer C, and I'm going to call this small volume, large port. And I'm going to check mark C, make sure that that's plotted. I'm going to hit calculate, and I'm going to go back to the model. So the light blue curve here was the results when the port didn't have any damping on it, but we did have a large port and small volume. The blue curve is now with the damping material covering the port, that resistive material, that 90 rail resistive material. If you notice, the major effect that material is having is it's lowering the Q on this resonance quite a bit. So it's a lot lower peak here, but that didn't have much of an effect on the pass band from 8 kilohertz down. It had pretty much a negligible effect at 8 kilohertz. So this lets us know that adding a material, at least upwards of 90 rails, won't have an effect on the frequency response of the microphone, but it will hopefully keep our foreign material out from getting into the microphone and causing any damage with it. Now that you've built your model, you can copy these model parameters out to the clipboard by going to Options and selecting Copy Element Parameters to Clipboard. I'm going to launch a notepad here. Aries will have copied the model parameters into the clipboard, and I'm going to hit Edit, Paste, And what you see here is all of the parameters from the model listed. So if you want to document it outside of a model, outside of an Aries model, you can do so by just doing that. So there's our model. We have achieved our results of pushing the resonance out of the passband, and that'll conclude it for now. If you have any questions about using the Aries modeler, please contact us at support@maellc.com, and we'll be happy to answer your questions.